You just saw was our robotic manipulator arm using forward, inverse, velocity kinematics, trajectory planning, and camera vision in order to pick up and sort different colored balls based on their color. In order for our team to get here, Team 17, we had to work through each step of the process. To understand how this works, let's go back to the beginning. Our robotic arm is the Open Manipulator X. It has 4 degrees of freedom, meaning it has 4 servo motors that each control one of the arm's 4 joints. If we want this gripper to be able to move to an object, like this duck, we just have to tell it to move down about 8 inches and over by 3, right? Well, not quite. The robot arm exists in what is called the joint space. The joint space is how the arm understands where it is. To move our robotic arm, we need to send each joint to a specific angle. And when we do this, it changes the position and the orientation of the gripper. And the gripper, or the end effector, is how the arm interacts with objects in this space called the task space. The problem is, when we see an object, we know its location in the task space, but the robot only understands joint space. So, to translate between these two spaces, we use what's called forward kinematics. Forward kinematics involves assigning frames to each of the joints and using geometry and the distances between the joints to find the matrices that move from one joint frame to the next. When we put all of the matrices together, we get a final homogeneous transformation matrix. By using the current joint angles and this transformation matrix, we can find the position and the orientation of the gripper within the task space. But we want the robot to pick up an object at a specific location, and that is where inverse kinematics comes in. Instead of calculating where the arm is based on its joint angles, we work backwards, figuring out the joint angles needed to place the gripper in the exact spot and orientation that we want to be able to pick up the object. We calculated the robot's forward and inverse kinematics and wrote functions in MATLAB to help us convert between the joint and task space. That way, we could tell the arm where to go in a way it can understand.
And that's how we started speaking the same language.
Just getting to the right location isn't our goal, so we implemented a quintic trajectory in order to ensure smooth and controlled motion of the robotic arm as it moved from one position to the next. Moving the robotic arm is only one half of the puzzle. The other half is using camera vision to detect the location and the color of the balls on the checkerboard. We use a standard USB webcam to capture the scene, but the camera has a fisheye lens, which distorts the image. To fix that, we use MATLAB's Camera Calibrator app to undistort the image. Once we've corrected the image, we apply a mask to the checkerboard to filter out any unnecessary objects. We then use color detection to classify the balls based on their color using different color masks. After that, we find the centroid of each ball in the camera's view, which gives us the 2D coordinates. We then use a transformation matrix to convert those 2D coordinates into real-world 3D coordinates that the robot can use to pick up the balls. We have a while loop running so that whenever there is a ball in sight of the camera, the robot will go pick it up and sort it by its color. With all these components coming together, forward, inverse, and velocity kinematics, trajectory planning, and vision, we have a robotic system that can detect, pick up, and sort different colored balls with precision.